So, hello and welcome to the last lecture of our course here. So, all the while that we have learned about linear time invariant systems, then nonlinear systems. So, we have studied about different features of the systems, and now we are going to actually study about a very important concept about any system, which is the concept of stability of the system. We need to understand about the stability of a particular system, whether it be linear or non-linear. We would adopt a more general framework here in this case and would try to see the non-linear and linear systems in the light of that framework. Now, stability would of course mean that we are trying to actually analyze the stability of an equilibrium point, because what we have come to understand that at no other points than the equilibrium points can the system remain where it is. So, a system remaining where it is the first criteria to satisfy, and then we must understand whether it will be there for any like for a small perturbation also. So, if it is able to remain at that same position, at that same equilibrium point, even in presence of perturbations, then that equilibrium point would be considered to be stable. Otherwise, it would be considered to be unstable. That means, if we perturb the system from the equilibrium point and then we see that the system does not come back to the equilibrium point, that means the equilibrium point is unstable. Okay. And we generally also refer it in this manner, that the system is becoming unstable. So, that is a very overview idea of what is stability. Now, to understand what is stability, what is actually happening, what is actually happening is the trajectories of the system is coming to a certain point and then staying there for all future times, and this certain point is, you can consider it to be the origin for the time being. Whereas for nonlinear systems, we know that it can be anywhere in the state space, but let us consider it to be at the origin for the time being. So, if the system is coming to the origin and then staying there for all future times, then we would consider the system to be stable. And so, this is the concept of stability of the system, not just the equilibrium point. So, then the system would be stable if it comes to the origin. However, if the system is going away from the origin, or it is going away from an equilibrium point, then the system would be considered to be unstable. So, in the state space of the system, so suppose this is the state space of the system, trying to draw a 3-dimensional one. X1, x2 and x3. So, if this is the state space and there is the origin is here, so what we are trying to see is whether a system starting from anywhere in the state space. So, let us have a system here that is starting from anywhere in the state space, it is eventually coming to origin or not. It can come in any different path. So, it is eventually coming to origin or not, that is what we have to test. So, what is this test? Basically, this test is basically looking at the vectors, looking at the state vector and trying to see how it is evolving in time. So at one instant you see that at t1 it is here, at t2 it is here, at t3 it is here, okay, because the states are what we have, the states are what we have from the dynamical system. So we can get the states from the dynamical system by looking at the evolution of the states, but that is by looking at the states at different points of time. Can we assess whether the state vector is actually going to origin or not? That is the question. So now you see, if you suddenly remove this trajectory, you are having these three state vectors. You are having these three state vectors. Now in a geometrical picture, by looking at these state vectors, you can perhaps say that yes, the t1, the vector at t1 is bigger than the vector at t2 and it is bigger than the vector at t3, okay. So probably the vectors are getting smaller and smaller and smaller. However, please mind it that a vector is not just a magnitude, it is also having a angle. So this orientation, where it is oriented, that we don't know. So we are only having, so when we are saying bigger and smaller, we are somehow in our mind, we are suppressing the information about the angle. We are suppressing the information about the angle and we are only considering the magnitude, which is perfectly fine, which is actually we should be looking at the vectors in that manner only when we are trying to consider whether the vector is coming near to the origin or not. Near to the origin, it does not matter in which direction it is coming, it only matters how far away from the origin it is. That means it is only depending on its length or the magnitude, correct. However, normally you will not see a geometrical picture like this. Normally you will find your state like something like a column vector, okay. So you will have numbers here, then suppose this is one vector, this is another vector, this is another vector, so now how would you say which vector is near to the origin or not? It is not very apparent by just looking at these vectors now, whereas it was apparent by just looking at the vectors in the geometrical picture. But when you are given in this manner, in numbers, in as column vectors, then you are not very sure which of the vector is nearer to the origin and whether I am progressing towards the origin or not, okay. So this is not very apparent by looking at the vectors in this manner, because in this manner the length and the angle information is not very apparent in this representation. So from this representation, actually if we can extract the length information, extract the length information L1, L2, L3, then perhaps we are at a position to compare the vectors as per its magnitude, or as per its distance from the origin. So we know that how we can calculate the length of a vector when it is given in the column vector form or column or row vector form. We know that we have to only take the elements, square them and take the square root. So in that way we can have an idea of the magnitude of the vector and we can compare them. However, if we generalize this idea of the length or the magnitude or the distance from the origin, So this is also distance from the origin, right? We can actually generalize this concept and formulate a function which is called the norm of a vector, and that norm of a vector function actually generalizes the property satisfied by the length of a vector. Let us look at this norm of a vector. What is the norm of a vector? Any function can be called a norm of a vector if it is a scalar function. So taking a vector, you are getting a scalar. So remember the length or the magnitude function also, and you will see that all the properties are satisfied by that function, the length function. However, any function which is satisfying all these properties will be called a norm of a vector. Norm is the more general term. So now the norm is basically, it is a scalar function first of all, and it is taking a vector, yes, from some domain in the which is a subset of the Rn space, and your norm, the function, is always greater than 0. It is a non-negative function. It is always greater than 0 for all x in the domain, and it is equal to 0 when if you have the norm equal to 0. That will mean that the vector is also the 0 vector. That means you have reached the origin. Okay, this slight change, to be very precise, one must say this, because the 0 is included in the domain. So x is greater than 0 for all x in the domain excepting 0, and when x is 0, norm x is also 0. So norm x equals to 0 will imply that x is also 0. That means you have reached the origin, you are at the origin. Another feature is this, that norm of Cx, where C is any real number, positive or negative, is basically mod of C norm of x. Remember, the length function also behaves in this manner. Norm of x plus y is less than equals to norm of x plus norm of y. It is the triangle, it is called the triangle property. This is a famous triangle property. So this is the x vector, this is the y vector, this is the x plus y vector, and the length of x plus y will always be less than length of x and length of y. It will be equal in the case when x and y are in the same line. Okay, so then that will be equal. What does the norm do? What does the norm do? The norm transforms a vector to a scalar, and we can arrive at conclusions for the vector using familiar ideas for scalars. The scalar is increasing or decreasing, we can say that the vector is also increasing or decreasing. So in this case, in the case of norm, so if the norm is increasing or decreasing, we can also say that the vector is increasing or decreasing. So these are the properties of the norm. Remember that it is always a positive scalar function. It is 0 only at the origin. Okay. So this actually gives us a handle now in order to understand the stability of a system or the stability of an equilibrium point. We needed to ascertain whether the vector is moving towards the origin or not. Now what we will ascertain? We will ascertain whether the norm is decreasing or not, whether the norm is becoming smaller and smaller and coming towards 0 or not. See here, it has become the norm. By doing the norm, we have actually collapsed the directional property of the vector totally. So it does not matter in which direction. So if this is the origin, then one direction is positive, another direction is negative. So whether it is in this side or this side does not matter, it only is considering the magnitude. Okay, so the trajectory might be like this, taking a spiral and going towards 0. So it is always looking at the magnitude, whether it is becoming smaller and smaller or not. Okay, so this is the norm of a vector. Now we will utilize this idea to understand the stability of the system, but before that we will see some norms which are very popularly used, and generally a general norm is constructed in this way. So any function which satisfies this sort of a this function, this expression is a norm, and it is a general p norm. P norm will mean that you take every element of the vector, you take the magnitude of every element of the vector, raise it to the power of p, sum over it, and then take a root of pth power. That is the expression of the p norm. Most used is the 2 norm, which is basically the length of the vector. This is what we are most familiar with, the length of the vector, which is the 2 norm. The 2 norm is the length of the vector. There are other some special norms which are sometimes useful and used as well, which are the 1 norm, which is nothing but the summation of the magnitudes of the elements of the vector, and it is sometimes denoted like this also, which is the modulus sign. The scalar modulus is there, remember it is vector modulus sort of a sign, but it does not, it means summation of the modulus of all elements, summation of the absolute value of all the elements of the vector. Another norm is there called the infinity norm. Infinity norm is nothing but the absolute value, nothing but the maximum absolute value of the elements. So there is a vector, suppose there is a vector -1 2 -4 1 0 3. So in this case you can calculate the 2 norm, you can calculate the 2 norm. I leave over to you how to calculate. What would be the 1 norm? 1 norm would be 1 plus 2 plus 4 plus 1 plus 0 plus 3, and this is 3 plus 3 6 10 11. Then infinity norm would be take modulus and see what is the maximum. So infinity norm would be 4 here. This is x, this. So in this way you can calculate the norm of a vector, and by noting down the norm or by working with the norm, we can arrive at the concept of stability. So now when we go towards the concept of stability, we are not limiting ourselves to the idea of the 2 norm or the length of the vector only. We will understand that we can take any norm depending on which is easier to use in a particular situation. Depending on which is easier to use at a particular situation, we can take that norm. However, since we are accustomed with the idea of the length of a vector, so when going through the theory, we would always keep the length of the vector in mind, so that we are able to understand the theory in a pictorial manner. Okay. So we are trying to ascertain the stability of the equilibrium point, and we would see that the theorems are talking about stability of the origin. This is because in any case, whether or not the origin is the equilibrium point or not, even if any other point in the state space is the equilibrium point, which can happen for nonlinear systems, the origin can still be treated as the equilibrium point for a general theory to be developed. because we can do a shift, actually a shifting we can do, which takes the equilibrium point to the origin. Wherever be the equilibrium point, it can be taken to the origin by a shift of the reference frame. How it is done? So suppose we have an equilibrium point which is not the origin, okay, but by the definition of equilibrium point, fx bar would be equal to 0. We keep this information with us. Now we do a change of reference frame. From the x coordinate we go to the y coordinate by simply making a minus x bar. So in all the x vectors we do a minus x bar. Then what would happen? The dynamical system in the y coordinates will be y dot equals to x dot minus x bar dot, but since x bar is a constant because it is one position only, single position, so it is 0. So x dot will again be fx. But now you can replace this x with y plus x bar, which you can say gy, a new function gy. It is a function of y only because x bar is a constant, it is not a variable. So it is a function of y only. Now you see that g0, when y is equals to 0, so g0 you try to evaluate, you will get fx bar which is equals to 0. That means in the system y dot equals to gy, which is the equilibrium point? Y equals to 0 is the equilibrium point because g0 equals to 0. That's why y equals to 0 is the equilibrium point. So in general, actually, even if the equilibrium point is not the origin, you can make a simple transformation like this and make the origin at the equilibrium point. So for going about the theory, we can actually assume that the equilibrium point, that the origin is the equilibrium point, and develop the theory of stability around this idea. So we are talking about stability of the origin. So now we are talking about stability of the origin, and we have to understand this is the stability of the equilibrium point. Any equilibrium point we have to ascertain the stability in this manner only. So what it is saying, the definition goes like this, that this origin would be stable if for each epsilon greater than 0 there exists delta depending on the epsilon, and this delta also greater than 0, such that norm of x0 less than delta implies norm of xt less than epsilon for all t greater than equals to 0. This sounds like Hebrew probably right now, but this is a very compact definition. Let us understand what it is trying to say. So let us take a two-dimensional picture right now for better understanding. Suppose what you are saying, what it is saying, you see the definition, what it is saying. It is saying that for each epsilon greater than 0 there exists delta greater than 0. So someone has given you an epsilon which is greater than 0. For this epsilon greater than 0, one must be able to find out a delta greater than 0, such that if you start within the delta region, so if your norm is within this delta, then norm of the xt is that the trajectory is evolving, right? For any t you can have the norm xt, but whatever be that t, the norm of xt will never cross epsilon, Now you shift your attention, you understand the norm as the length, and then we can develop a picture here. If you understand the norm as the length, then what it is saying, that you have been given an epsilon circle in case of two-dimensional system. In case of a general n-dimensional system, this is called the epsilon ball, delta ball. This is called a ball. This is the n-dimensional ball. Okay. So you see, this is the ball. This is the epsilon ball. So you are trying to ascertain whether my trajectory will never leave the epsilon ball or not. For that, you must be able to find out a delta ball from where you must start. So you must start, x0 must be within this delta ball, anywhere in this delta ball it can be. Suppose in this point, at this point x0 is, so this is your x0. If you start from this x0, what it is saying is that your trajectory will never leave the epsilon ball. It can go like this, but it is never leaving the epsilon ball. This is what it is saying. The system behavior is such that the trajectory or the system is confined to an epsilon ball, and in order that might happen, we have to find a delta ball from which the system must start, the system must begin. The initial condition must be within the delta ball. So if we are able to find such a situation, then we would call the system to be stable. Why? Very intuitive, because the system is near about the origin. It is not going far away from the origin. You are able to confine the system within the epsilon ball near to the origin. And you see that the trick here is the language. Each epsilon greater than 0. Each epsilon greater than 0. So you are allowed to take your epsilon as small as possible. You are allowed to take your epsilon as small as possible or even large if you wish, but for all these epsilon, you must be able to find a delta. For all the epsilon, there should not be one epsilon for which you are unable to find a delta, right? So any epsilon ball you may fix, larger or smaller, you would see that you will always be able to find an initial ball or a ball from where you might start, and your trajectories will be within that epsilon ball. So if you may have a larger epsilon ball, then it doesn't make so much sense, because you are allowing your trajectories to be larger and larger. So you have to make the epsilon smaller and smaller and see till when you will be able to satisfy this stability consideration. So this is the idea of stability, and this is also called Lyapunov stability. Lyapunov stability. When it will be unstable, it is unstable if it is not stable. That means you are not able to find any epsilon. You are not able to find any epsilon ball such that from somewhere you start and you will be able to confine your trajectories within that epsilon ball. This means what? The trajectory will eventually escape to infinity. That's the reason you are unable to find any epsilon ball for some initial condition. So, for any initial condition, basically your trajectories are escaping to infinity. That is why it is unstable. So, your origin, even if origin is the equilibrium point, so you have to actually have a delta which is greater than 0, not equal to 0. Okay, your epsilon is also greater than 0, not equal to 0. That means you have to start from somewhere near to the origin, not exactly at the origin. So, if you start somewhere near to the origin, then you will not be able to find an epsilon ball in which your trajectories will be contained. That is why it is not stable. And in the first case, if you start near to the origin, there would be some epsilon ball in which you would be able to confine your trajectories. So, it is stable. Now, the last one, which is asymptotic stability. Asymptotic stability is saying that it is stable. First thing is that it has to be stable, and on addition to it, you can choose your delta in such a way that starting within the delta ball, your xt would eventually become 0 as t tends to infinity. That means this trajectory would be like, the trajectory would be like this. So, it can go out of the delta ball, but eventually it will come to the 0. That is the thing, as time tends to infinity. So, this is stable because it is not going out of the given epsilon ball. Additionally, it is coming to 0. So, it is asymptotically stable also. So, if it is only stable, it is called Lyapunov stable. If it is asymptotically stable, it is asymptotically stable. And it is unstable if it is not stable. So, that means you are unable to find any epsilon ball in which your trajectories will be confined, no matter how small the delta is. Okay. So, that is the case there. Example, a very common example is the pendulum system. The vertically down position is only stable when damping is absent, because it will go on in a simple harmonic motion. So, it is like the trajectories are never escaping beyond a certain region. So, you can confine the trajectories within a ball, and actually in the 2D state space it is a circle. So, this epsilon ball, it is not living. The vertically up position is unstable because you cannot actually find any delta greater than 0 such that the trajectory can be maintained within a given epsilon ball. You fix your epsilon balls, but you will not be able to find any delta ball from where you will be able to start and keep the trajectory within the epsilon ball. This means that by a very small perturbation at that equilibrium point, you will actually be unable to contain yourself near to the equilibrium point. You will go away from the equilibrium point totally. So, that is the vertically up position. Vertically down position is asymptotically stable when damping is present. So, when damping is present, we know that the vertically down position, it will eventually come to the equilibrium point. So, as time tends to infinity, the trajectory converges to the origin. So, it is asymptotically stable in this case. So, all the three types of equilibrium points are found in the pendulum system. Now, Lyapunov stability theorem. Now, stability theorem is basically what it is trying basically is to ascertain whether a system is stable or not. Now for linear time invariant system, we know that we can find the eigenvalues and it will give me the stability, but for nonlinear systems there is no concept of eigenvalue. So we have to actually simulate the system and look at the trajectories, look at the phase portrait for two-dimensional systems. So all these things we have to do in order to ascertain the stability. But Lyapunov stability theorem says that we don't need to actually compute that state trajectories. We don't need to do that. We don't need to simulate the system. We can actually do some algebraic calculation and try to ascertain whether the system is stable or not by following this theorem. So what it is saying, it is actually asking you to construct a positive definite function v. So this function is also looks almost like the norm. If you pay attention, this is also a scalar function. This is also 0 at x equals to 0 and greater than 0 for all x in the domain excepting 0. So it is at par with the definition of the norm. Okay. Additionally, we are trying to ascertain whether the time derivative of this function is negative semi-definite or not. Negative semi-definite means less than equals to 0. So you are actually, what you have done, you have constructed a positive function, and a positive function which is 0 at the origin. So suppose this is the base level or the origin level, and it is positive outside the origin. Anywhere outside the origin it is positive. So it is almost like a potential function. If you understand what is potential energy, it is almost like that potential energy function. It is 0 at a reference point, which is the origin here, and it is positive at everywhere else. If you are able to prove that the time derivative of this potential function is less than equals to 0, suppose it is less than 0, it will be easier. First is less than 0, that means at everywhere in the space the potential energy is getting reduced. At everywhere in the state space, for all x in D, so for everywhere in the state space the potential energy is getting reduced. So it means that eventually you will come to the origin, because eventually potential energy will get reduced and it will come to 0. After 0 it cannot be lesser than that, because it is the least. So it will come to 0 and it will stay there. So this is how Lyapunov tried to ascertain the stability of a system by constructing a potential function like this, which is called the Lyapunov candidate, actually Lyapunov candidate function. So function satisfying these properties are Lyapunov candidate functions, and function satisfying this property is the Lyapunov function. So if you have a Lyapunov function, then your system would be Lyapunov stable. This is Lyapunov stable because it is having less than equals to 0. Less than equals to 0 means it is the Vx, the potential or this energy function is decreasing, but somewhere it becomes constant. It is decreasing, but here at somewhere in x in the domain of x, this v dot x becomes 0. So it comes here and sticks here. So it is not reaching the origin, but it is confined to some epsilon ball around the origin. It is bounded in some region around the origin. That's why it is Lyapunov stable only. However, if you find that v dot x is absolutely negative, definite, then you can say it is asymptotically stable. In that case, v dot will be 0 only at x equals to 0, and in all other places it would be less than 0. This means from everywhere in the state space, your trajectories will be such that it is trying to reduce the Vx, it is trying to reduce the Vx because v dot x is less than 0. So Vx is trying to be reduced, and by the nature of Vx, it is least when it is at 0. So it will come to 0. The trajectories from anywhere in the state space will come to 0. This is anywhere, it is not anywhere, it is within from a region D, from the domain D. So you are talking about a domain. So in a domain D, you are testing for all the trajectories, and you don't have to simulate, you only have to construct a function like this and then test whether the v dot, whether the time derivative of that function is negative for in this domain also. That is what you have to ascertain. So an example wise, or what I can say, suppose that, so one v you can see Vx equals to x square. Suppose we have taken Vx equals to x square. Does this satisfy the first property? Is it a Lyapunov candidate? By looking here, you see, yes, it is a Lyapunov candidate. Now you have to see what is v dot x. V dot x is what? 2x x dot. 2x x dot is v dot x. Now x dot is what? X dot will come from the system dynamics. Suppose your system is this. Suppose your system, let's see. Suppose your system is x dot equals to minus x cube. This is a nonlinear system. You are not able to readily understand whether this is going to be stable or not. So you did a analysis like this. You took a Vx equals to x square, v dot x is 2x x dot, and you replace x dot here, it will become 2x to the power of 4. And you see that this is less than 0 everywhere apart from the origin. So this is asymptotically stable, right? So this is how you actually utilize the Lyapunov stability theorem. We have to remember that this is only a sufficient condition. That means if you are able to find out a potential, find out a energy function or the Lyapunov function like this, and you are able to see that v dot x is less than 0, then you can say that it is stable. But suppose you have taken some other Vx here, which is also a Lyapunov candidate, but v dot x is not coming to be less than 0. This will not mean that it is unstable. This will only mean that you cannot actually ascertain anything about the stability right now. Your friend may have devised some other Lyapunov candidate function for which v dot x will become less than 0. But you have not able to find out that Lyapunov candidate function. So if you are unable to find out a Lyapunov candidate function for which v dot x is less than 0, it does not mean that the system will be unstable. It only means that there may be some other Lyapunov candidate function which you have not considered. It can also mean, right, it can also mean that the system is unstable, but you will not be able to conclude this from the fact. So from the fact that v dot x is greater than 0, you will not be able to conclude that it is unstable. Okay, so this is a shortcoming of the Lyapunov theorem we need to remember. Now you might have many questions in your mind right now, what is the base, how to select the Lyapunov candidate, can we always find out Lyapunov candidate? So there are some methods, though we must remember that it is almost like a trial and error, and there are some methods by which you can actually figure out some Lyapunov candidate functions, but they are a bit involved also, and you don't need to go through all those things for this purpose of this course. So you need to understand this much only about Lyapunov stability theorem. And there is also, so this theorem here, this was limited to a domain, and if you have if you have this, actually if your D becomes, actually this D should be here Rn. So I have copied from the previous slide, so I will not change this. D should be Rn here. So if your function is from Rn to R is a positive definite function as well as radially unbounded. Radially unbounded means that norm x tends to infinity, means Vx also tends to infinity. Norm x tends to infinity means my vector has gone to infinity. This implies that your function Vx is also infinity. So this is radially unbounded nature. So if your Lyapunov candidate is radially unbounded, and even then you are seeing that v dot x is less than 0, then x equals to 0 is globally asymptotically stable. It is globally asymptotically stable now, not in a local region, not in a domain D. It is globally asymptotic stable. In the entire state space it is asymptotically stable. That means from the entire state space, you start from anywhere in the state space, you will come to 0 eventually. It is also called asymptotically stable at large. And in this case, if this is the situation, if origin is globally asymptotically stable or asymptotically stable at large, then it is the only equilibrium point. Then the origin is the only equilibrium point. Because if you had any other equilibrium point, you would go there and you would stay there, or if you have started from there, you would stay there. So the Lyapunov stability theorem would not fit, would not be valid in that case. So if the Lyapunov stability theorem is valid, then the origin would be the only equilibrium point in the case when it is globally asymptotically stable. Now we have used the terms positive and negative definite for the functions, and you have understood what that is. Basically it is either greater than 0 for all the domain of x, it is less than 0 for in the entire domain of x. Now actually we can construct these sort of functions using another idea about positive and negative definite matrices. So normally this function x square, this is a positive function, we know it's a positive definite function. when we come to the vector case, this is nothing but xtx, x transpose x. This is also a positive definite function. This is the equivalent of x square. Now in the vector case, actually we can also include a matrix inside. So the quadratic function, this is a quadratic function, x transpose px, p being a real symmetric matrix which is positive definite or semi definite. Sorry, it is saying in this way that the quadratic function, this quadratic function is positive definite or semi definite if and only if all the eigenvalues of p are positive or non-negative. So when you include the matrix P here, then this entire function's positive definiteness depends on the positive definiteness of the matrix P, and the matrix P is basically positive definite if the eigenvalues are positive. If it is positive semi definite if the eigenvalues are non-negative, that means some zero eigenvalues are also possible. So the matrix P, you see, is called positive definite, and we can write this. Okay, so this is a bidirectional thing, if and only if. That means if the matrix is positive definite, this function is positive definite. If this function is positive definite, the matrix P is also positive definite. Okay. Now about negative definite. So if this function, where we have this P or Q as real symmetric matrix, please keep this in mind, these are real symmetric matrices. It is negative definite if this function is negative definite if and only if V equals to minus x transpose qx is positive definite. So if x, we will call x transpose qx as negative definite if minus x transpose qx is positive definite. Similarly, semi definite, negative semi definite if minus xt qx is positive semi definite. In this case, Q will be called a negative definite matrix, and we would write Q less than 0. It will be called a negative definite matrix. Okay. So so to ascertain whether a matrix is negative definite, we are not checking the eigenvalues of the matrix. We are checking the eigenvalues of the minus of that matrix basically, and whether they are positive or not. That means a matrix with negative eigenvalues is not actually given the definition of negative definite. We are actually coming to the positive definite matrix and defining the negative definite matrix. So if a matrix, if minus q is positive definite, then q is negative definite. If minus q is positive definite matrix, then q is negative definite matrix, and we write it as q less than 0. So q less than 0, p greater than 0, this will mean that these are positive matrices, positive definite matrices, not negative definite matrices. Stability of LTI systems. Now using the Lyapunov theory, there is the stability of LTI systems can also be defined in a very as a necessary and sufficient condition. So for For nonlinear systems, it was only a sufficient condition, but the same theory applied to linear time invariant systems gives you a necessary and sufficient condition. What does it say? So you have a positive definite Lyapunov candidate, that means XTPX, where P is a real symmetric positive definite matrix. This is a Lyapunov candidate for the system x dot equals to Ax. So you calculate the derivative. By calculating the derivative, you get this, and that you write as this. That means you replace PA plus A transpose P with minus Q, So here P transpose is not there because it is a real symmetric matrix. Okay, so P transpose and P are same. So this equals to minus Q. So Q is a symmetric matrix defined by this equation, which is called the Lyapunov equation. So this equation is called the Lyapunov equation. So if what I need V dot x less than 0. I need V dot x less than 0. So V dot x is equals to minus x transpose qx. This I need less than 0. That means I need Q to be greater than 0. Q I need as a positive definite matrix. So if I have a Q as positive definite matrix, for that I can solve a P which is a positive definite matrix given the A I have, then the system will be stable. So you see, you read this statement, if Q is positive definite, we can conclude that the origin is asymptotically stable. That means the matrix is Hurwitz or a stability matrix with eigenvalues having negative real part. How to find out, how to go about with this theorem? We first fix a Q which is positive definite, and for that we solve a P. We solve the P and check whether it is positive, negative or not. We don't do the other way. That means we don't fix a P and then evaluate PA plus A transpose P and see what that matrix is. We don't do it that in this manner. We go do the other way, because if you fix a P, it might so happen that you are not able to find out, or your Q is not coming out as positive negative as positive definite. But by the Lyapunov theorem, you know that if you are unable to establish this fact that V dot x is less than 0, that does not mean that it is unstable. But in the case of LTI system, we have some advantage, because it is coming in this manner, the Lyapunov equation is coming in this manner, and we want Q to be positive definite so that V dot x is less than 0. So we fix Q as negative as positive definite from beforehand, and then we find out what is P. And now the solution of P, if it is positive definite, then we are absolutely sure that it is stable, and if it is not positive definite, we are absolutely sure that it is unstable. So now we actually land in a, we actually land in necessary and sufficient condition. Yeah, I have mentioned it here, necessary and sufficient condition. So what we do, the check is whether there exists a P greater than 0 satisfying the Lyapunov equation for a chosen Q greater than 0. For simplicity, many times you will see Q equals to I could be chosen. This is could, not cold. This is could be chosen. So this is how we go ahead actually. So if you have a LTI system, you would know the A matrix, There are two possibilities. You calculate the eigenvalues or you solve the Lyapunov equation. Which is better? There is no particular advantage in any of this. You can either solve the eigenvalues or solve the Lyapunov equation. So there is no particular advantage, there is no particular advantage in any of this. However, the advantage in going through the Lyapunov function is that you would get the P matrix. And now if this LTI system is a linearized system about a reference point, so you know linearization now. So if you have linearized the system and you have found out a P matrix for the linearized system, then you can use the same Lyapunov function for the nonlinear system also to ascertain the local stability of the nonlinear system, local stability in the region only. So you can utilize this Lyapunov function in the actual nonlinear system. You can use this Lyapunov function and see whether your V dot is coming to be less than 0 or not, or it is less than 0 under some conditions, maybe. So you will be able to understand the stability conditions of the nonlinear system in that case. So it gives you a Lyapunov function candidate straight away. And this makes us come to the Lyapunov's indirect method. So previous one was direct method. Now this is the indirect method where you actually ascertain the stability of a nonlinear system by looking at the stability of the linear system, linearized system. So if you have a linearized system and you have the A matrix now, then the origin of the nonlinear system is locally asymptotically stable if all eigenvalues of A have negative real part, and origin is unstable if one or more eigenvalue is having positive real part. So you have to only ascertain the stability of the linearized system. So this is talking about the eigenvalues. You can also solve the Lyapunov equation. So if you have found the system to be in the Lyapunov equation, you have found a solution, that means that all the eigenvalues have negative real part. That means the actual nonlinear system is locally asymptotically stable. If we have found that there is one eigenvalue, at least one eigenvalue which has positive real part, or in other words, if the Lyapunov equation is not giving you a solution of P to be greater than 0, then you can say that it is unstable. This is what I have written here, that you can do the Lyapunov analysis of the linearized system by simply verifying the solution of the Lyapunov equation. So if you have found out, if you have evaluated this P so suddenly not writing, I don't know why. Okay, some lag is there. Okay, this P, if you have found out to be greater than 0, then you can say that the nonlinear system is also stable, locally stable. And if you have your P to be not greater than 0 or less than 0 or less than equals to 0 like this, then you can say it is nonlinear system is unstable. And how to check this? So P greater than 0, you have checked it is not P greater than 0, that means all the eigenvalues are not positive for P. So you check for minus P, if all the eigenvalues of minus P are greater than 0, then P is less than 0, or if it is greater than 0 or 0, then it is less than equals to 0. In that case you will have unstable situation. So this is the case, and the same thing you can do actually by looking at the eigenvalues of A matrix directly also, that is also fine. So this makes us come to the end of our lecture as well as the end of the course. So the Lyapunov analysis is a very important analysis for nonlinear systems as well as linear systems. It is very widely used in actually in modern control systems where we represent systems as in state space representation. So this is very useful and one should know about this thing. So with this I come to the end.